Hi, my name is skj180001 and I am in Professor Karami's CS4337 class, section 001, and my presentation is going to be over the topic of return-oriented programming and looking at a research paper that addresses this topic. So the paper that I have chosen is titled Return-Oriented Programming, and it was written by Marco Prandini and Marco Remilli from the University of Bologna in Italy. In this paper, they discuss, well, one, the importance of the integrity of the execution slash control flow, or the stack, and delve into buffer overflow errors and how these could be exploited by return-oriented programming techniques. Finally, they also discuss countermeasures to these exploits, ranging from operating system-based techniques to compiler-based defenses. So first, I'm going to be talking about the general basics of return-oriented programming, or ROP, and just give you some context of it. So essentially, return-oriented programming is a class of security exploits where attackers execute unauthorized code by manipulating and interfering with the execution or control stack. And so in particular, it's known as return-oriented programming because of its exploitation of the RETN assembly instruction or return command, which essentially drives the process control out of the process flow. And in this case, that's the attacked process flow. And then it returns to the previously called address. And so this ability to move to a specific memory address or cell is vital for this exploit to work. And so when attackers create a buffer overflow, they can choose what is in that data cell that's run next by the return command. And so through this, they can run whatever code they want on the target machine. Also, each of these instructions that end with the return command are known as gadgets. And so by chaining a lot of these instructions, or gadget chaining, the hackers can write or run any piece of code, even if they haven't directly added anything externally into the memory of this machine. And so there are two primary ways that, or two primary classes of ROP attacks. The first is injecting malicious code. So in this, essentially, the attacker is bringing in and adding their own code into the stack of the machine. And then the other class is code misalignment. And in this case, what the attackers are doing is they're basically modifying and chaining, with gadgets, existing code to create new malicious code. So here we have an example of how code misalignment can work. And in this case, if you can see my cursor, we have the normal alignment from 89 to 08. And so that would be the stack and how the flow usually goes. So by changing the order that these pieces of code are called, or like the pieces in the stack are called, you can that process is called misalignment, and so you can chain it in a different way than the actual alignment and run whatever other algorithm or code that you want. And so here's an example of gadget chaining where you have two gadgets, and so you have like the two addresses of the gadget on the stack. The way it's structured is you have the first gadget's address, then all the data that the first gadget needs, and then the return jumps to the second gadget. And so in that way, they're chained together. And so now moving on to some countermeasures. Again, there are two primary classes that are discussed in this paper. The first is operating system-based countermeasures. And in this case, the first one is called data execution prevention, or DEP, and this is primarily for preventing attacks where intruders are trying to inject their own malicious code into the stack. And so in data execution prevention, or DEP, you essentially have a flag that demarks set memory at a memory address range as being executable or not. And so this flag just stays with the memory management data structure in place. And so, for example, since the stack is not supposed to have executable code, it just has addresses to such code, the OS can set the stack's DEP flag to 0 when it's initialized. And this essentially allows the OS to reject any attempts of jumping and fetching instructions from the memory area if attackers are able to inject their code into the stack itself. Because, again, there should not be executable code in the stack itself. And then, however, there is a potential to sidestep DEP by using gadget chaining, as discussed before, or code misalignment. And so with code misalignment, since the gadgets that are needed are already in the executable memory areas themselves rather than the stack, they are able to circumvent the DEP policy. And actually, a common implementation of ROP attacks is to disable the DEP policy by causing a jump to the function that sets the DEP policy and setting it to 1 instead of 0. So basically allowing the stack to execute instead of not. And then once they've basically disabled DEP, they can use existing buffer overflow attacks and injecting code and running that again. And another method of defense actually in this case is randomizing memory allocation. And so with this, Microsoft actually introduced this with asynchronous space layout randomization, or ASLR. And in this scheme, there's essentially randomized mapping from physical to virtual memory. And so it's harder for attackers to exploit the buffer overflow since it's more difficult to know exactly which memory locations have the instructions that they're trying to call. So again, as mentioned previously, code misalignment can overcome the effectiveness of DEP by disabling the DEP policy. And now we're moving on to some compiler-based defenses and looking at detection. So one pretty straightforward way of defense is just to have a trigger that detects any unusual number of retin calls, because again, since ROP attacks are kind of centered around the RETN instruction and executing that to multiple areas of the stack, if there is a trigger in place to alert the user whenever there's an excessive number of retin calls, this could allow the computer or the machine or the human, if anyone's using it, to know that there's an attack going on right now. And then the other countermeasure is called gfree, and in this it essentially eliminates all unaligned free branch instructions inside of the binary executable, and therefore protects the aligned instructions from misuse by attackers. But then the drawback to this is that it's only 100% effective when all developers are using a patched compiler to build applications. Because again, if it's a compiler based and detecting during runtime, the developers need to have the most up-to-date compilers. And so, in summary, this article goes over how ROP attacks exploit weaknesses in the control flow. And something that I've learned as well is the importance of the integrity, right, of the stack and the control flow. And it also discusses that there are operating system and compiler-based defenses, but attackers have been getting better and better at evading them and continuing to successfully exploit vulnerabilities. And finally, any future countermeasures and defenses that are going to be made will need to be devised by both operating system designers and software engineers to be truly effective. Because again, this problem uh, targets these exploits target so many aspects of a machine that there needs to be checks in place all throughout. So now coming to the article itself, I personally thought that it was a very effective article. It gave a lot of great information in a relatively short space. Some examples are that I thought that it presented the basics of ROP really well to the point where someone like me with absolutely no clue that about cybersecurity or these kind of attacks still understood it just because of my knowledge of stacks and such. And then I also personally really liked how that the article detailed countermeasures and also how those defenses were kind of broken down in a sort of back and forth manner. And so this allowed me to better understand the various concepts involved in control flow integrity and how if there's a defense that's devised in this one area, an attacker could go somewhere else and still continue to attack. A prime example of this is how uh, gadget chaining can be used to overcome DEP policy, right? And continue to use the original attacks, which are just quicker in a way. And finally, I thought the article it had a lot of credibility because of the various papers, experiments, and such that it used to back up its points. Also, the images and sources that it had were also really great at illustrating the context that I needed. Uh, and an example of this would be like the reference to a paper by Shacham that proved that misalignment could produce a Turing complete language, and so attackers would be able to uh, generate any algorithm or piece of code that they wanted from existing material. There were also some negatives or places of improvement that I found. For example, I think the article would have benefited from more context about the rest of the security field. And I realize that like it is an article about return-oriented programming, but I think just expanding the context a little bit would have been more effective in just giving a bigger picture, right? I also think that like real-world examples of the attacks and the kinds of systems that were affected would also be really helpful in, again, just going from theory to practice and just a better helping readers better understand where and how these might be applicable in their lives. Finally, I thought that at the end of the article, the authors do say that for future countermeasures, it's not just going to be operating system designers, but actually, since attackers have been managing to devise like a system of variable exploits that can delude a lot of detection systems, in the future, operating system designers and software engineers are going to need to work together to better protect their system and buttress them from these attacks. And while I think that is a great point, I think there could have been a better prescription on how they might achieve that, or what kind of solutions that they might look at. Right. I think also they could have included other research taking place at the moment and in the near future about the topic to give their points about future improvements more credibility. Yeah, and finally, I think that this article really helped me understand like that the control stack and buffer overflow vulnerabilities are real places of weakness, and that we will need to. Again, this article, I think, show that ROP is a rising class of attacks, and attackers are only getting better and better. And so there does need to be a lot of research in the field to develop very secure and strong countermeasures. And also that, for the industry as a whole, preventing these attacks that are so widely prevalent would greatly benefit the security and trust we have in our devices. Right. So thank you for listening.